Okay, so this week's lecture is on serial communications. So we should be learning how to talk to the computer and to other devices as well. So this is basically how you expand the functionality of your Arduino. So one of the most important things is talking to the computer. So one of the is an excellent way of debugging, basically. You can make it do more useful things, send data back, and both read data in. So the Arduino's got built-in USB ports that you've been using to program it. But as well as programming, it allows you to just send text backwards and forwards. They call this is just standard serial interface. Sometimes you'll see it called UART, UART as well. They're basically exactly the same thing in this context. So yeah, you can also use this to talk to other things like Wi-Fi modules or GPS modules tend to use this as well because they come out in a human-readable format. So this is a basic piece of code for talking to the computer from the Arduino. So in your standard setup, you call serial.begin, and then this is your baud rate. So that's the number of bits that it transmits per second. The USB communication is what's known as asynchronous, so there's no clock line, so you have to set both of them to exactly the same baud rate, otherwise it will just come out with complete and utter nonsense. This serial.println, or println, will just print out whatever you put in it, followed by a new line. So if you just want to dump stuff out to your screen, that's a really easy way of doing it. Just throw it out, and then it'll just turn up on your Arduino system. If you've all got the IDE open, you'll see in the top right of the window somewhere there's something that looks like a search button, like a little magnifying glass. That is the serial monitor. That is the window you will use to actually communicate with your Arduino using this. Yeah, so this code carries on. You've got serial.available, which will tell you simply if you have sent characters from your computer to the Arduino. If it's 0, there's none there. If it's anything above 0, that's how many characters it's actually read in. So this piece of code is just waiting for you to type something. There's a bit of a delay on this one, just to make sure you finish sending everything. Now this one is a serial print. Now the difference between print and println simply is this one doesn't put a new line at the end. So if you keep calling print, it'll just carry on across the same line. This now reads in. This is just the standard loop that you should have seen before in the other lectures. But it basically, this one is counting down, which is the difference. So it starts at how many characters are available and counts down until it's read them all. This is doing a very simple thing. It's just storing the value read from the serial port using serial.read into a character and just printing it out. And then it's just printing a new line at the end so they can loop around without piling everything on one row. You should have some code for something like this, so you can try it out in a bit. Yeah, so you should have all this code. We'll test it out in a bit, and you can get it actually working, sending stuff backwards and forwards. So yes, there's two different methods of communicating, basically. You can either have a serial communication or parallel. The USB port, or the UART, is serial, as well as the SPI and I2C that we're going to be using later. This basically means that it sends it one bit at a time. So it's just in a single line, one single cable connection between the two, and all the data just goes through sequentially. The other option is parallel communication, where basically you have one line for each of the bits you want to send, and you send them all at once. Parallel is, in a theoretical world, faster, but it's not the way that most of the memory works. So it's quite difficult to actually implement this. Sometimes, some of the things you'll see will still run in parallel, but most of this stuff, in fact, all the stuff we'll be looking at today is serial communication, and most of the things you will use basically ever on an Arduino will be serial. So basically, these will be communicating in binary. And if any of you can figure out what that is, then it's probably a word of some sort. So binary, simply each character is either a 0 or a 1. This is standard way electronics work. Inside all the microcontrollers, even if you're using a word, doing literally anything, it will be stored in binary on there. So each bit in the binary number is one of these characters, basically. So 1 or 0 is a bit. If you get 4 of these together, they're called a nibble. And if you have 8, it's a byte. The Arduino runs pretty much everything in bytes. It's an 8-bit microcontroller, so everything is in byte sizes. There's also 16 bits, which is a word, which is used for integers, and other microcontrollers will run on that. So what this allows us to do is it stores the values as each of these bits represents a different number. So if this is 1, then you add 1 to your total. This one is 1, you add 8. So these are all just in powers of 2 increasing. So the way you figure out what number this actually represents is you just add up all of the numbers that correspond with a 1. So you add up the 1, the 2, the 8, the 64, and the 128, you end up with your 203, which is the number it's actually storing. This is how it works actually inside the microcontroller, and when you're transmitting through serial, it will transmit 1 bit at a time. Generally, most of this is all wrapped up in the microcontroller for you, so you don't have to worry about it, but there will be certain applications, like the shift registers we'll be looking at next week, where you will actually be looking at the individual bits for what you need to do. So another useful thing is binary shifting, which are these operators here. The 2 arrows, they literally just take your binary number and they shift it to one side or the other. If this is nicely animated. So that is a binary right shift of 2. So it took the number and literally just moved them all to the right. That is the equivalent of dividing by 4. So effectively you're losing the bottom 2 bits of the resolution and moving it all up. This is useful for very specific things, talking to devices, and if you're trying, and is what it actually implements if you're running a division on there. So, let's jump back a bit. If you guys want to have a shot at doing the first serial example that we've got on the sheets, talking to the computer, getting your text going backwards and forwards, we'll get that going to begin with. Okay, so the next thing we're going to be discussing is I²C, which stands for Inter-Integrated Circuit. So this is a communications protocol like the serial protocol you were just using, and it's used to communicate between different circuits in your system, between different chips in your system. So it's designed as what they call a multi-master system, so they can take it in turns to be masters and reply back to things. Yeah, this one, unlike the serial port, uses 2 lines on here, but they use them in different ways. So what you have is you have a data line, the SDA in this case, stands for serial data, and SCL, which is the clock line. So the data line can have data going in either direction on it, and the master is generating a clock. This means that you don't have to set the bit rate in the same way as you did before, or the baud rate. So the 9600 you had at the top of your code is setting the baud rate. This one, they will all synchronize because you have set it on the output of the master. Now, because you've got several devices attached together on the same bus, they all have to use an address. So each of these will be identified by an individual address, so you can talk to each one separately. Yep. So in your kits, you should have a chip with an I written on the back of it, on a little breakout board. This is an I²C temperature sensor, more specifically the LM75A. Yeah, so as I was saying, I²C uses 3 lines if you're including ground to transfer the data and the clock. Yes, the LM75 stores its temperature in 2 bytes, or as an integer in this case, within its internal memory. So you need to be using the bit shift tools that we said about a minute ago to actually recombine this into a number when you read it through. Yeah, so this should animate at the bottom. So when you first read it in, your I²C read function, wire.read in this case for the Arduino libraries, will work in exactly the same way as the serial.read. It will read in 1 byte, put it into whatever variable you have in the first 8 bits available. But because we want to read out 2 bytes, we need to recombine it. So we have to shift that along so that it doesn't pile on top of each other, and then we read in the 2nd byte. This allows us to combine them together and get them out in the actual data format we wanted. The way this is actually stored is specific to this chip. They'll all be different. You can look up on their data sheets how they actually will store this information. Some of them like to store it in little bits scattered around all over the place. You have to recombine them in the right way to actually get something useful out of it. Oh, Apparently you have to shift it right by 5 again. Yes, so this one you have to shift right by 5 again because it's got these 5 dead bits in it, basically. They have no useful information in it whatsoever, so you just shift it off so they fall off the end and are discarded. So this is the code you should have on your sheets. The diagram is a little hard to read, so I'll leave it on the screen when you're having a go at it. What this is designed to do is it will just simply read out the temperature and print it out to the screen using what you have used before. So the serial setup is exactly the same. The serial.print is the same as you've been using before. The extra bits you've got here, you've got an integer for the device address. You've included the wire library, which is the I2C communications library. So it does a lot of the work for you, has written a lot of code in it, allows you to just communicate with I2C devices a lot more easily. Yes, so you've got the device address. This is unique to each chip. In this case, this chip has 3 pins on it that you can use to select 3 bits of your address. So you can have up to 8 of these devices attached together, and they can each have a different address. As with most of these things, you need a .begin function in your setup. That just configures it and turns on the outputs on the Arduino. And then you get into the actual talking to the device bit. So in I2C, you send requests to get the data, basically. So in this case, you use wire.requestFrom, the address of the device you want, and how many bytes you want it to send you. So we want the first 2 bytes out of it, which are the ones that contain the temperature. Then, simply put, we store this into a word, which is 16 bytes, bits rather. 16 bytes would be huge. And you store in the first bit you read, shift it by 8, then add on the second byte you read. And then we do the shift by 5 to get rid of the useless data off the end. And then we print it out to the serial port. Now this factor we have here is to convert it into degrees Celsius. This is on the data sheet for the device. They'll all be different. But that's just turning it from the binary value that's stored inside of it into an actual human readable value. And this is pointing out something with the serial print function, that now we're just feeding it an integer, and it will convert it into all the ASCII characters so that you can just read integers on the screen, rather than transmitting it in binary, which would be useless. Yeah, so if you guys want to have a quick go at this, it should be fairly easy to get the temperatures read out. I'll leave this on the screen because it's quite hard to actually see on your handouts. Okay guys, so we're going to just go through the next bit, and then you can all just play with whatever you've got lying around, what you want to actually get working. So the other sensors you've got with you with the S written on the back are SPI sensors. This is serial peripheral interface. Again, this is for communicating between chips, but it's a lot more complex. So as you can see on this diagram, you have your master, and you've got your slave devices. So your slave device in this case is the other temperature sensor you've got. It communicates using several more lines. Again, you've got a clock line so that it synchronizes all of your data across all your devices. That's the same. But it has this MOSI and MISO. These are your data lines. They stand for master out, slave in, and master in, slave out. So what this means is that it can transmit data to and from the device at the same time. And hence you can do everything a lot faster. Terrible timing. The other pin you've got here is this SS pin. This is the slave select pin. So rather than using the addresses like you had in the I2C to select your device, this one you actually set a pin. So for every slave device you have another pin on your master to select it. This can be both good and bad. This protocol allows you to communicate a lot faster than I2C, but you're limited to how many you can connect simply by how many pins you've got on the Arduino. Because for every extra sensor you attach, you need another pin to be able to control it from the Arduino. Yes, so although all of these things have names like I2C and SPI, there are a lot of things that will pretend to be these. So yeah, so there's things called microwire, which is just SPI, or it can actually, there are things that will say they're 1-wire compatible or 2-wire interfaces, which may or may not work properly with your SPI or I2C, whichever one they happen to line up with. So there's something to watch out for when you're getting components. They may say they work with these things, but they don't necessarily line up properly and interface everything that they say they do. because the Arduino library is set to interface in a certain way. It's set to do it properly, but some of these devices implement a slightly different way. As it says at the bottom, luckily you can bit bang these, where basically you just cheat, don't use the libraries, and you just write it from scratch yourself, just toggling the pins up and down. And that means that you can talk to all these ones that aren't quite the standards and do slightly different stuff. So the other chip you've got is a TC77. It's another temperature sensor chip, but this one just communicates over the SPI. So we're doing very simple configuration on this. We're not doing anything too complicated with it because we just want to read out the temperatures. It does have a lot more features, like I believe this one has an alarm on it or something like that. So it will set a pin if you reach a threshold, but don't quote me on that, that might be a different chip. So the TC77 does 16 bits, so it does it in 2-byte chunks. The first 12 bits, the ones with the data in it that we actually need. So this is a simplified version of what you'll find on the data sheet for the sequence of actually talking to it. So this is the steps you need to do. So you set the clock pin low, set the chip select low so it knows which one to talk to, and then on the clock and your data lines you transmit your data and receive your data, and that's basically what this is showing at the bottom with an oscilloscope. So you've got your chip select line at the top, your clock, and your data line. And this is basically just how it communicates. This is what we've translated into the code that you've got here. So the SPI is a slightly different setup to I2C. There's slightly more to do when configuring it. So what we have to begin with is we set up which pins we're using for our interface. Some of these, I think these two are set in hardware. The slave select you can do whatever you like with, and pick any pin. The default, I believe, is 10, but you can pick whatever you like because obviously if you have more than one device, you need more than one pin for it. Yeah, so for SPI, is he bit banging this? Yeah, so we've set up the clock pin, the slave select pin, and the data pin. That's just setting them up as our outputs and our input to read the data back in. And then literally through here, we're just using the digital write functionality in the loops you've seen before to implement that system that was shown on the previous slide. So we set the clock pin low and high, which gives it the rising edge it needs to catch it, and then we just read in the data off our data pin and store it into our data variable. So this double shift I is bit shifting the data we're receiving into the next bit along every time we read one. And then once we finish the transfer, we turn off the chip select line and then we print it to the output like we were doing before. So this isn't actually implementing the SPI library because this is one of those SPI sort of sensors. So this doesn't actually behave properly with the SPI library from the Arduino website, but the Arduino library basically handles most of this stuff for you, allows you to just read and write to it in the same way as the wire library. But this gives you a much better understanding of how it actually works. Yes, so unfortunately we missed that bit in the datasheet when we were buying it, hence the cautionary tale of problems with these things. So if you want to have a go at this one, you should have this example code. Hopefully that diagram is readable enough. And then if you've got that one working, there's a couple of challenges. I know some of you have been having a go at some of these already. See if you can get some more complex functionality out of these.